I'm going to do a quick review of all the work on surds that you should know already. So this is a review. Just quickly defining surds. Basically we're looking at expressions where we've got this sign here. That's a square root, but it's not always square roots. Okay, it applies to other roots, nth roots. But basically root A is the general form. By the way, that is called a radical, that sign. A is a rational number that is not a perfect square. If it was a perfect square, we'd get an integer value for the square root. Okay, so we're looking at those sort of things there, and we've got some examples further below that we can see. Okay, so examples: root 2, root 3/4 are examples of surds, and they're irrational numbers too. In other words, an irrational number is not possible to write down completely in decimal form. That's an approximation there for root 2. It's not the exact value. It's not possible to write it as an exact value because it doesn't ever terminate. Okay, it doesn't terminate and it doesn't repeat. That makes it irrational. You can't write it as integer over integer. Okay, so that's no pattern. Nothing repeats, nothing recurs, and it never ends. So that's why we need things like square root 2, or just say root 2, because that's the exact value. It's not merely the decimal approximation. And we need to be able to do operations on surds. We're starting here. So if we multiply two surds together, we can equate that with the product of the two together. Then we take the square root or the nth root on it. Likewise, it works the same with division and quotients. So please note that if you have forgotten it. And looking at some examples below. Okay, so we got root 36 divided by root 2, which we can write like this. And root 36, using that first law we just saw above there, if we can go 9 by 4 is 36, we choose 9 by 4, or I've just thought that, hold on, 36 is actually a perfect square. So let me pause. Apologies, I was just about to make that much more complicated than I need to. 36 is a perfect square, so it's not a surd over root 2. Now I could write that with a rationalized denominator. I'm going to show you that in a bit more detail in the rest of the video, but I could do this, multiply it by root 2 on root 2, because root 2 on root 2 is equivalent to 1, or when you multiply something by 1 the overall value doesn't change. So we have multiply the two numerators together, we get 6 times root 2, or 6 root 2. Root 2 times root 2 is 2, so 6 root 2 on 2, or in other words 6 divided by 2 is 3, so we've got 3 times root 2, which we write as 3 root 2. The second one, root 2 times root 5 times root 10, and that equals root of 2 by 5 by 10. And 2 by 5 is 10, 10 times 10 is 100, that's the square root of 100, which is not actually a surd, it's an integer value 10. And the third one, root 32 times root 2. Now keep the root 2 as is, and if we go 16 times 2 here for root 32, we can then split that up, root 16 times root 2 times another root 2. Okay, because 16 plus 16 is 32, so 16 by 2 is 32. You can split those up. Now root 2 times root 2 by definition is 2. Square root of 16 is 4, and we've got 8 as our answer there. What I'd like you to do now is to pause the video and try this one and include the full solution in your Cornell notes. When you're finished, hit play again. Another example, 8 root 2 times 3 root 5 times root 10. So we've got 8 lots of root 2 times 3 lots of root 5 times root 10, which I'm going to change to root 5 by 2, 8 root 2, 3 root 5. I'm going to split up root 5 and root 2. Now, if we look at collecting things that are alike, we can see the root 2's, we can see the root 5's, and so when we multiply them together, the two green root 2's make 2, so we've got 8 times 2. Alright, I'll keep that there, and we've got root 5 times root 5, which will be 5. And I haven't included that times 3 yet, so I've got to do that. The order is not important. And we've got 8 times 2 is 16. So we've got 10, multiplying all that together, 240. That's what I get there. Basically, with surds of the same root can be added or subtracted, just like algebra can. So if we look at that one there, we've got square root of 8 minus square root of 50. Let's see what we can do about that. So we've got 25 by 2 for 50. Now we've got 4 by 2 here. I'm going to split the 25 and the 2 up. So we've got square root of 2. Now square root of 4, we can rewrite that as 2, but square root of 2 stays as root 2. So we've got 2 root 2, and 5 is 5 is the result of the square root of 25, and the root 2 stays the same. So we've got just law up here. We've got 2 lots of root 2 minus 5 lots of root 2 is negative 3 lots of root 2. So when we're simplifying expressions that contain like surds, contain surds, we basically see if there's common factors. We can take a factor of 6 out of that, that, and that. So that's all the terms covered. So if we divide top and bottom by 6, we're simplifying that. So that'll be 1 plus 2 root 2 over 1, because I've taken 6 out, or in other words 1 plus 2 root 2. So that's simplified. Okay, lastly, rationalising the denominator is where we get a non-surd value on the denominator. That used to be super important in the pre-calculator era, but it is still important now, and sometimes when you want to check the answer in the back of the book, it will be written with the denominator rationalised. So the idea is to times the fraction by 1, but there are infinite number of versions of 1. If we've got something like 1 on root 2 here, basically if we times it by root 2 on root 2, that's actually equal to 1, isn't it? And what you do, you times the numerators together, we get 1 times root 2. We multiply the denominators together, we get root 2 squared. We get root 2 on 2. So it's got the same value. Okay, and more complicated one here. What would we times this one by, because it's got surds on the top and the bottom? Well, basically we would multiply it by, you look at the surd on the bottom, on the denominator. Okay, that's where it's at, the denominator. So we go root 3 on root 3. Okay, multiply across, we've got root 3 root 2 times root 3. Whoops, that's a 3. And over 2 times root 3 by root 3, which is root 3 squared, isn't it? And that's 3 root 6 over 2 by root 3 squared is 3. And we've got 3 root 6 over 6. And now we can divide top and bottom by 3. So that's root 6 on 2, or half.